Welcome back. The next part of this section is about something called homogeneous systems. And a homogeneous system of linear equations is a system where the right-hand side has only zeros in it. So the augmented part, the right-hand side, on the right-hand side, the equal sign, it's all zero. So 3x plus 4y plus 7z equals 0. X minus y plus 2z, 0. Like all of the right-hand sides are 0. Those types of systems are special, they're important, and they have some nice properties. A system that has some of the right-hand side being non-zero, so let's say equals 2, equals 10, equals -8, we would say that's a non-homogeneous system. So in these three examples, we're asked to classify them. Are they homogeneous or are they not homogeneous? A is homogeneous. The right-hand side's both 0. They're already in standard form. How about B? What do you think? Homogeneous, not homogeneous? Well, it's the coefficient part that we need to have on the left-hand side and the constant part that we need to have on the right-hand side. So this one needs to be rearranged. We need to transform it, subtract y from both sides, add z to both sides, and do the same thing for the second equation. Add 3x to both sides, subtract 2y from both sides, put them in standard form, and we see that it's homogeneous as well. The last one, we do the same transformation, we bring it to standard form, and we see that one of the equations, the fourth equation, has an equals 4 on the right-hand side. That means it's not homogeneous. That's just classifying them based on whether or not they're homogeneous. Automatically, as soon as you see a system of linear equations is homogeneous, there's a guarantee that there is at least one solution. And that solution includes, or rather must include, 0. So x is 0, y is 0, z is 0 if you're in R3, all the variables being 0. You can think about y. So let's think of this equation right here. If you replace all the x's and y's with zeros, left-hand side will equal right-hand side. You'll get 0 is equal to 0. Same thing for this one up here. We replace the x's and y's in both equations with 0, you get 0 is equal to 0. So it's automatically a solution. But it's not going to be a solution for this one here. Replacing x and y with 0, you're going to get, in the third equation, 0 plus 0 is equal to 4, which is not true. So automatically, a homogeneous system cannot have no solution. It has to have at least one solution. It could have a family. It could have only one, but it cannot have no solution. So here's a little bit more about why that's the case. Homogeneous systems, all being 0 on the right-hand side, means that the rank of the coefficient matrix must be the same as the rank of the augmented matrix. The right-hand side being all 0 means you can't introduce an additional leading 1 by having a non-zero number inside that entry and a 0 number here. So we're either forced to have the situation where the rank of the matrix, we're forced to always, for a homogeneous system, the rank of the augmented matrix is always going to be the rank of the coefficient matrix. What will distinguish homogeneous systems from each other is whether those ranks are equal to the number of columns or if they're less than the number of columns. In the first case, it means there's only one solution, that x, y, and z are all 0. And then in the second case, it means that there's a family of solutions with one or more parameters. So we have an n by n matrix with rank A. We're told that it's homogeneous, and we can classify it as having a unique solution if that rank is equal to the number of columns, and it'll have a family with n minus p parameters if the number of if that rank is less than the number of columns. So if any of the columns are missing a leading one. So an example on the left-hand side is if the rank of A equals the number of columns. So rank of A is 3, number of columns is equal to 3, unique solution. X is 0, Y is 0, Z is 0. But the ones on the right-hand side, they're all a family of solutions with a varying number of parameters. Here we have, I'll circle all leading ones in all these cases. Here we have the rank of A equals the rank of A augment B equals 3. Number of columns is 5. Check the time. Thus, 5 minus 3 is equal to 2 parameter family. Next one, rank of A is 3. I should say it's the same as the augmented matrix. The number of columns is 6. Thus, 6 minus 3 is equal to 3 parameter family. And the last one, rank of A equals the rank of the augmented matrix, which is 2 because we have 2 leading ones. Number of columns, we have 1, 2, 3, 4, 5, 6, 7 columns. Thus, 7 minus 2 equals 5 parameter family. And on this slide, it just shows you how you would write that in terms of the conversion process that we used using different labels. So putting parameter labels for everywhere where a parameter label is needed. Something else to note about homogeneous systems is if you ever have more columns than rows, then that means that you can't possibly have a leading one in every column, because every leading one has to exist in its own row. So let's say you have 3 rows, 5 columns. At most you can have 3 leading ones. That means that such a homogeneous system is going to have a family of solutions. And you can tell how many parameters it's going to have by what the deficit is. So in that case, it would be 2, the deficit of 2 leading ones. So based on what's shown for these examples, we're going to just summarize whether the system has unique solution, family of solutions, no solution, or if we need to do work. So how quickly can we diagnose it? First one is homogeneous. It has 2 equations and 3 unknowns. So the homogeneous part means not no solution. We can exclude that from being possible because we can't have 0, 0, not 0 since the right hand side is 0. 2 equations and the 3 unknowns means max rank is 2. Since the rank is the maximum rank is the smaller of the number of rows and number of columns. That means that we're guaranteed that this is a family of solutions. Must be family of solutions. How many parameters? It could be 2 parameters, it could be 1 parameter. We can't tell without row reducing. Maybe you can stare at that a little bit and tell, okay, it's 1 parameter, but maybe not. You'd have to row reduce to tell for sure. The second one, we have, it's not homogeneous. Well, I said homogeneous, homogeneous. I'm trying to, homogeneous, not homogeneous, homogeneous. It's not homogeneous, so it could have no solution. It has 2 equations and 3 unknowns. that means it cannot have a unique solution. Tell it right away. You're going to have a deficit of leading ones. At least one column will be missing a leading one. At least one column is missing a leading one. So we don't even have to do any row reduction to tell that this is going to have a either no solution or family of solutions. We would need to row reduce this in order to tell which is which. How about the next one? Well, it's homogeneous. So it cannot have no solution. Cannot be no solution. It has to have either a unique solution or a family of solutions. But we cannot tell the rank without row reducing. Also, 3 equations and 3 unknowns, 3 variables. So potentially can have a leading one for each column. So this one's either a family or unique. And then the last one, it's row reduced. Three equations, 6 unknowns, not homogeneous, and we can tell it's going to have a family of solutions. Family with 1, 2, 3 parameters. So some of these we could tell very easily, some of them we have more work to do, like the third one we'd have to reduce to tell for sure. So as a summary of sorts, there's a collection of statements in matrix algebra that are all equivalent to each other, and we're going to add to this list. If a matrix A is square, so n by n, then the following statements all mean the same thing. They're all equal to each other. They're all identical statements. That if you're told that A is an invertible, so if A is an inverse, then it means the matrix has full rank. You can convince yourself why. Full rank means every column has a leading 1. Since it's a square matrix, every column being a leading 1, after row reducing means you can row reduce the matrix to the identity matrix. If you can row reduce the identity, you can row reduce the matrix to the identity, then it means that you can do A bar identity row reduces to I bar A inverse. I'll write that down. Since we can complete A bar identity goes to identity bar A inverse. Since it's square, okay, that's just, sorry, A being invertible means that we can complete that. So that's equivalent to saying it's full rank. Every column gets a leading 1. That's what full rank means. which the identity matrix looks like that when you row reduce it. The row reduced echelon form of A is the identity matrix. Well, that's again using the same idea that if A is invertible, then you must be able to row reduce A to the identity matrix in order to go through that process. Well, I mean, if we said that A is invertible, then that means that the system has a unique solution, since X is equal to A inverse times B. We could also go back to the rank idea. The matrix having full rank means every column has a leading one. So that we've already established that means that there's a unique solution. And then the homogeneous system AX equals 0 only has a trivial solution. That's using A inverse times B. X is equal to A inverse times the right-hand side times 0. 0, 0, 0. That's going to be 0, 0, 0. All these statements are identical to each other. So, concrete example. Select all the statements that are true if you're told that A is a 5 by 5 matrix with rank 5. This means full rank. Every column has a leading 1. If every column has a leading 1, when we row reduce it, that means that we can row reduce the original matrix to the identity matrix, which means we can create A inverse. B, is that one true? This is false. X equals A inverse times B. So, unique solution. So not B. C, the matrix, the SLE in B must have a unique solution. That's true. And D, the SLE in B could have no solution. We need to reduce to find out. Absolutely not. Rank of A equals N means rank of A comma B is equal to N as well. You cannot have a larger rank by adding, or you can't exceed the a rank large. You can have a rank larger than the number of columns. It doesn't matter, like adding another. What am I saying? Number of rows, rather. So you have 5 rows. You have a rank of 5. Adding another column does not allow you to add another leading 1. You need another equation as well. So augmenting doesn't add another equation, it just adds another column. So the only things that are true are A and C. Anyway, that's it. See you next time.